Right now, drifting somewhere in the dark between the stars, there is a planet with no sun, no orbit, no star to circle, just a world alone, moving through the galaxy at hundreds of kilometers per second, with nothing above it but the cold of deep space. We call objects like this rogue planets, and for a long time the assumption was simple. No star means no heat. No heat means no liquid water. No liquid water means no possibility of anything resembling life. That assumption is almost certainly wrong. By the end of this video, you'll understand how a planet survives without a star, why the inside of a rogue world might be warmer than you'd expect, and why one specific rogue planet, a world roughly the size of Jupiter, detected drifting alone through the Milky Way, has forced scientists to rethink what the word habitable actually means. And there's one detail about rogue planets that almost nobody talks about, something that changes the calculation entirely, something that has nothing to do with the planet's distance from a star, because there is no star. First, what a rogue planet actually is, because the name sounds dramatic and the reality is stranger. Stars form from collapsing clouds of gas and dust. As the central star ignites, the leftover material flattens into a disk around it. Planets form inside that disk, accumulating material over millions of years. Most of them stay. They settle into stable orbits, held by the gravity of the star they formed around. But not all of them. In young solar systems, the gravitational interactions between forming planets can be chaotic. A planet that forms too close to a massive neighbor or gets caught in the wrong resonance at the wrong time can be flung outward, past the outer planets, past the edge of the system entirely, out into the open galaxy. No gradual drift, a hard gravitational ejection launched into the dark. And once a planet is gone, it doesn't come back. The galaxy is too large and too empty for a second encounter to be likely. That world becomes a rogue, drifting indefinitely, its original star shrinking to a faint point and eventually disappearing into the background noise of 100 billion others. How many rogue planets are out there? The honest answer is, we don't know precisely, but the estimates are staggering. Some models suggest there could be more rogue planets in the Milky Way than there are stars. Not slightly more, potentially several times more. Every ejection event in every solar system over billions of years contributes to a vast, cold, invisible population drifting through the galaxy undetected. We've confirmed only a small number directly, because finding a planet with no star to illuminate it is extraordinarily difficult. They emit almost no visible light. They don't transit anything we can measure. The only way to find most of them is through gravitational microlensing, detecting the brief, characteristic brightening of a background star when a rogue planet passes in front of it and bends the light. The signal lasts hours to days and never repeats. You either catch it or you don't, which brings us to the specific world that changed the conversation. In 2011, a survey of gravitational microlensing events detected a statistical population of Jupiter-sized objects drifting freely through the galaxy, not one or two. A population implying they were common. The data suggested roughly 2 Jupiter-mass rogue planets for every star in the Milky Way. That number has been debated and refined since, but the core finding held. These objects were out there, and there were a lot of them. Then, in 2021, a rogue planet candidate was detected through microlensing with a mass closer to Earth's. Not a gas giant drifting alone. A rocky, Earth-sized world. Alone in the dark, with no star, no system, nothing. That shifted the question, because a Jupiter-mass rogue is almost certainly a frozen gas giant, interesting in its way, but not the kind of world you associate with warmth or complexity. A rocky Earth-mass rogue is different. A rocky planet has a surface. It has an interior, and what that interior does is the part almost nobody talks about. Here's what actually keeps a rogue planet warm. Not the surface, The surface of a rogue planet without a star is roughly 70 degrees below 0 Celsius at best. In deep space, away from any stellar radiation, the temperature approaches the cosmic background temperature, about -270 degrees Celsius. Nothing liquid survives on the surface. The surface is dead by any reasonable definition, but the interior is different. When a planet forms, it accumulates enormous amounts of material through constant collisions. That process releases heat, a lot of it. The Earth's interior is still warm from its formation 4.5 billion years ago. That residual heat, called primordial heat, bleeds out through the planet's surface over billions of years. On Earth, it contributes to volcanic activity, tectonic movement, the whole geological engine that keeps the surface dynamic. On a rogue planet, there is no star adding heat from above, so the surface radiates that interior heat into space and cools faster. But deeper down, in the mantle and core, the heat persists. And in more massive rogue planets, there's a second heat source, radioactive decay. Elements like uranium, thorium, and potassium-40 sit inside the planet's rocky interior and decay slowly, releasing heat over billions of years. This is not a negligible contribution. On Earth, radioactive decay accounts for roughly half of the total heat flowing from the interior. On a rogue planet, it's the primary ongoing heat source, and it doesn't require a star. It runs entirely from the inside out, independent of anything external. Now add one more element, a thick atmosphere. A rogue planet that retained a dense hydrogen and helium atmosphere during its ejection would have something extraordinary. A greenhouse effect with no star to power it, just the planet's own internal heat radiating upward and being trapped by the atmosphere above. Models published in the last several years have explored exactly this scenario. A rogue planet roughly the size of Earth or larger, with a thick primordial atmosphere of molecular hydrogen, could maintain surface temperatures above the freezing point of water. Not comfortably warm, not tropical, but above zero. Liquid water, potentially stable, on the surface of a world with no sun. Not for 1,000,000 years, for billions. Here's what makes this genuinely disorienting. We define the habitable zone as the range of distances from a star where liquid water can exist on a planet's surface. The inner edge, too hot. The outer edge, too cold. The narrow band in the middle, the Goldilocks zone, has been the organizing principle of the search for life beyond Earth for decades. Rogue planets break that framework entirely. A rogue planet has no habitable zone because it has no star. It generates its own heat, traps it under its own atmosphere, and maintains liquid water through mechanisms that have nothing to do with stellar distance. If life can exist on a rogue planet, the habitable zone as a concept stops being a universal filter. It stops being the thing that determines where life is possible. It becomes just one of several mechanisms that can produce the conditions life needs. And that reframing has a consequence, because if rogue planets outnumber stars by even a modest factor, and if some fraction of them maintain liquid water for billions of years, then the number of potentially habitable environments in the galaxy may be far larger than our star-centered models have assumed. Not slightly larger, potentially orders of magnitude larger. Most of that life, if it exists, would exist in permanent darkness under a thick frozen surface layer, warmed from below, never seeing a sky. But existence doesn't require a view, so here's where that leaves us. Somewhere in the Milky Way right now, and almost certainly more than one somewhere, there are planets drifting alone through the dark. Some of them are gas giants, cold and frozen, remnants of solar systems that threw them out billions of years ago. But some of them may be rocky worlds with liquid water in the dark, kept warm by the slow decay of elements that have been releasing heat since the universe was young. No star, no orbit, no light from above, just heat from below, an atmosphere holding it in, and time. Billions of years of it. We built our definition of habitable around a star. The universe, it turns out, didn't have to.